All right, this is the beginning part of Unit 3, Day 8. We're looking at real-world functions and something called exponential growth, using some exponential functions and models and things. We're going to be talking about some applications. So there's some real-world problems we're going to look at in this lesson. Okay, the first thing I want you to do is to do this warm-up, do these 4 problems where you're going to evaluate each of these given functions for a specific number. And you can pause the video to be able to give yourself time to do those. When you have all 4 answered, you can click play and check your answers. If you need more time, pause, but this is what you should get for each answer. All right, we should get 6 when f is evaluated at -2 here. You can see where I plug in -2. We should get -7.5 when I plug in -3 for g here. That one doesn't work out really nice and neat, but when I do -3 times a half, that's -3/2. And then what -3/2 is like -1.5. -1.5 minus 6 is -7.5. And then for number 3, when I plug in 10 for n here, we get 12/4, which is 3. And then when I plug in -12 for x here, we get 40. So now we're going to take a look at interpreting exponential growth. Okay, and we're going to talk about what that means. Okay, in our first example, we are told to consider these functions. That just means think about these functions, and we're going to see which one increases more quickly as x increases. So we're going to kind of look at what happens here. Our first function, f of x equals 2 times 3 to the x. And then our second function, g of x equals 3 to the x plus 1. Okay, I want you to look at these pieces and remember back to last lesson. Both of these pieces have a common factor for our exponential model here, or a common ratio of 3. Okay, that means we're multiplying by 3 each time. All right, but the problem we have here is they have some different parts thrown in also. This 2 here, sorry, common factor was 3. This 2 here is what we would call just our 0 term. Okay, and this one doesn't have a 0 term, or it does, but the 0 term is just a 1. So that doesn't tell me how much more quickly this curve goes up. The exponents are going to tell me that, and this one's kind of tricky to look at, but this exponent is just x. This exponent is an x plus 1. And so this function is the one that's going to increase more rapidly or quickly because of this. So we're going to write this, g of x, because the exponent in this is always 1 more than the exponent here. Okay, it's always 1 more than the exponent there. So that's always going to be just a step ahead of this function. So it increases more quickly as we move left to right on a graph. Okay, same kind of idea here. Look at our bases, okay? And we're actually going to take a look at this one in class, mainly because we really need to be able to graph this, okay? So we're going to come back and we're going to talk about this one together in class. But we need to be able to look at the graphs using our graphing calculator. All right, so let's take a look at example 3. Okay, we're going to be able to graph a real world function. I'm going to take my graph here and I'm going to do all of these things. I'm going to do it one step at a time. Okay, first, this is the real life situation. Suppose that Sam receives a gift card to AMC movie theater. It costs him per visit to the movies. So this is a function we could have to represent this gift card. Okay, where v is the value on the gift card at any time relative to the number of visits in, okay, meaning how many times he goes to see the movie. All right, so this is a very important piece. You'll notice that this is going to be linear because it follows that mx plus b. It's just kind of written backwards. So we're going to graph this function just basically by making a table of values. Okay, we're going to look at it as if n were the number of visits and V of n is how much is left on the gift card. Well, if he uses, we're actually going to start at 0. Okay? If he uses the gift card 0 times, if he doesn't go, there is $100 on the gift card to start with. Okay? Because I do 10 times 0 is 0, 100 minus 0 is 100. But if he uses the gift card once, that would be like 100 minus 10 one time. So 100 minus 10 is 90. And if you use it twice, that'd be a total of 100 minus 2 movies, or 80. And then 70 for 3 movies, so on and so forth. So we're going down $10 from our total 100 every time. So what we have to do is be able to plot our axes as my V of n axis here and my n axis here at 0, 0. I don't need any negatives. I can't go to the movie negative number of times, and I can't get negative dollars. Okay, so we're just going to start plotting these points. When he visits 0 times, he had $100. So I got to count my lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what I can do is my V of n, every line can be $10. Okay, or I could skip a line and count by 2s. So there'd be 40, 50, 60, 70, 80, and then there's 100. So that's, actually I'm kind of running out of room. That is where we start. When he visits the movie 0 times, or sees 0 movies, he has $100 on the gift card. We're going to drop down 1 every time we go over. And even though I only went to 70 here, I could keep going all the way down until I run out of room. So this is graphing the function. Okay, we need to label the axes in the scale though. So this is 1 movie, 2 movie, 3 movie, 4 movie, 5, 6, 7, 8, 9, and so on and so forth. Okay, so this is the number of movies. Okay, this is the amount on the card, or the value of the gift card. So you've got to be able to label and number your axes. Okay? And that's what the scale is. Scale is giving the numbers, labeling is with words. So part B says, what is the initial value of the gift card? Well, that's what he started off with. That's $100. Okay, that's this part. What is the constant difference in the value of the card before and after he uses it? Okay, well, that's that amount we're dropping down each time. Constant difference is negative $10. He's subtracting $10 every time he uses the gift card to see a movie. I want to identify the domain and range of my function here. Well, my domain is all the possible number of movies he could see. Now, I could write this out a couple different ways, but my easiest way to write this out is using set notation. So the domain starts at 0 movies. He could see 0 movies, but it goes all the way up to, if my graph continued over 1 more, he'd run out of money at 10 movies. And then the range that goes with that, okay, we start all the way at the end here with $0 left on the card, but when I started at the very beginning, I had $100. We always go least to greatest. So there's your domain and range. Now, is this linear? Yes, it is. We said that at the very beginning. It's a linear function. Yes, because of the common difference. Okay? That common difference of negative 10 makes us linear. So my final question here is kind of confusing at first. It says, are the outputs an arithmetic sequence? Why or why not? Well, we've talked about that before. If these outputs are an arithmetic sequence and there is a common difference, that is always linear. So yes, the outputs are arithmetic sequence because it's linear. Or because of the linear pattern. All right, let's go ahead and take a look at the rest of the notes on the other side. Okay, in example 4, Sue has a $20 gift card for music downloads. Each song costs $2 to download. The amount of money left on the card can be represented by the function m of d equals 20 minus 2d, where d is the number of songs that she's downloaded. This is very similar to what we just did in the previous example. So I'm going to do part of this in the video, and I'm going to ask you to pause to do some of this on your own. So the first thing we want to do is make a table for our graph. Part A is we're going to make a table and graph this. Part B is going to answer this question. So what I want you to do is choose some domain values. Now I don't want to use things that wouldn't exist in this real life situation. Can she download a number of negative songs? No. Or a negative number of songs? No. Can she have less than $0 on the card? No. That's not how gift cards work. So we have a set of information that has to fit in this upper right quadrant, or quadrant 1 of our graph. No negative numbers. So I don't want to start with negative numbers for my D values, the number of downloads. I want to start with the very minimum she could have, and that would be 0 downloads. And I want to continue on increasing by 1 download at a time, just to start the chart here. Now I might have more options than this, but that's a starting point. And so what we want to do is start plugging these in and coming up with our output. And I'm going to let you pause the video and do that on your own. When I plug in 0 for D into this function rule or formula, what do I get? Okay, these are the answers you should get. If you need more time, pause the video, but this is what you should get. Okay? We get these values for my output, and I can start writing these as ordered pairs. And so what we want to do, again, we want to make a graph. I want to label this axis as my output axis, or my M of D, using that function notation. And this axis is my D, my downloads. Okay, we only download in increments of 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth, with this being 0. But then we always want to make sure we include the right scale for our output. The highest value I go to is a 20. If I count it by ones here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I can't get all the way up there. In fact, I wouldn't be able to get most of these outputs on the graph. So I'm going to count by 2's instead. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I'm just going to count by 2's for every line. And really, I don't have to go any higher because that's my highest value I have. So I start plotting these points, 0, 20, 118, so on and so forth. It looks like my scale is dropping down 1 every time I go to the right, but remember I'm counting by 2's. So your common difference there is -2. Okay, so we've graphed our function. Now we need to identify this. We want to identify the domain and range of the function and explain that relationship that they have on the situation. So what we're going to do is we're going to list our domain. Our domain goes from 0. You could see that the next line down should be able to get to 10 songs. 2 times 10 is 20. 20 minus 20 is 0. Okay, so it goes all the way to 10 songs. And I kind of said it as I was writing it. The domain refers to how many songs she can download. Okay. So she can download 0 to 10 songs. All right. Now let's talk about the range. The range goes the lowest lowest amount of money on the card is $0 all the way up to the original starting value of 20. So we go from 0 up to $20. And again, I've said it as I was explaining it. This means she can only spend $0 to $20. So these little sentences I've written afterwards explain the relationship that the domain and range have on the situation. When you take your test, you're going to see things worded like this, so it's really important you get familiar with that in these examples.